Okay, so we're going to talk about just the concepts behind what you need to do to deal with finding limits analytically. So this just means you're doing it with algebra or with math, right? Instead of graphs or tables or anything like that. So first thing that you're always going to want to try is direct substitution. So that would be just like plugging the number in, So your example, if you had f of x equals 2x, if we plugged in 2, if we were looking at the limit as x approaches 2, we would just get 2 times 2, which is 4, right? Which is good. Yay. If direct substitution fails, if you get 0 over 0, which we call this the indeterminate form. If that happens, more work must be done. So you've got several things that can go on from there. So let's look at those. So our first thing that could happen is you could use this dividing out technique, which would involve factoring. So this would allow us to solve for something that we couldn't previously have done. So like if we had an equation like this, x times x minus 1 over x, right? If we were looking around 0, right, we'd be dividing by 0, we'd be multiplying by 0, and so we couldn't evaluate this. Well, if we were to factor and figure out, okay, well, x is actually a factor of the numerator and denominator, then we can cancel these out, and we're just left with x minus 1, which now we can plug in. So that's one strategy. B would be a strategy called rationalizing. Now, this is going to be when you see square roots, okay? So you may see it as something like the square root of x, or excuse me, the square root of x plus 1 minus 1 over x. Right? You may see something like this, to where if we were to plug in 0, we would get 0 over 0 again. Well, once we rationalize, and rationalizing is all about finding your square root, and you're going to multiply by the the conjugate of that, which is the same thing, but with a plus sign, or a minus sign, depending on what you have first. So it would be something like this. So we're multiplying by 1, so we're not changing anything, but we're going to eventually get rid of this square root. And that's going to be very, very helpful to us. And then you're going to eventually divide out. So you're going to be going back to the dividing out technique after you rationalize. So this is a longer problem. C. C would be if you are working with trig functions. Then you're going to use trig identities. Now there are two very important trig identities when it comes to limits. One of them is the limit as x approaches 0 of the sine of x over x. So this, if you were to plug in 0 into these, you would see that you would get 0 over 0, which we call that indeterminate form. Well, that means there's more work to be done. We can't really work with this anymore. It's not really, we can't really divide anything out. We can't really rationalize. But it's helpful that this is just a law. This is just always true that the sine of x over x as we approach 0 is 1. It's just a rule. It's just true. Then we have our second one, which is the limit as x approaches 0 of 1 over the cosine of x. Now, for this one, the oops, the cosine of x, or yeah, this answer is going to be 1 as well. And we can actually find this by directly substituting, because the cosine of 0 is 1. So these two concepts will be used in our next video. Sorry, this is not a law. This is just true all the time, which I guess makes it a law as well. But we're going to use these two in our videos, our example problem videos next. Now, the last thing that we want to talk about is called the Squeeze Theorem. This is just an idea, kind of a logical idea that I think you all will find pretty easy to understand, and the math tends to make sense. If, let's say, we have a point C that exists, and it goes all the way up, so some point C, and we're going to be looking at the limit as x approaches C of some function h of x. Okay, so we'll be looking for h of x in a second. So let's say we have a function f. So f looks like this. Nice and smooth curve, no big deal. Okay, so we've got our f. And then we have this other function, which is going to be g. Now g is a function that is always lower than f. So always lower than, it can be equal to, but it's always lower than f. So this is g, and this is f. Okay, so this is a true statement. Now, if I knew of another function, which we will make this yellow one, if I knew of another function that was always lower than f, but always bigger than g, okay? So, if it's always lower than f, but always bigger than g, so we'll say h of x, then we would have this situation here. Well, what if they were all equal to each other? Which it seems that they are at this point C, right? They all hit, okay? Well, if I knew that the limit as x approached C of f of x was, we'll say, some number L, and I also knew that the limit as x approaches C of g of x was also L, meaning that their limits match, then that would infer that, or that would infer that the limit as x approaches C of h of x is also L, because in this situation that we've defined, if this function is always less than or equal to f of x, and g of x is always less than or equal to h of x, which is less than or equal to f of x, if these two functions equal each other, then that means that this function must also equal them as well, and therefore its limit must also be there. So the idea is that if these two outer functions that we know about squeeze together and meet, and we know that this other function has to be between them or equal to them at all times, then we can therefore infer that this function also has the same limit.